Good afternoon, everyone. So, this session we will continue with what we started yesterday. So, we are looking at frequency domain representation of continuous time signals. So, we saw that these complex exponentials e power j omega t or e power st, they have specific nice property with respect to linear time invariant system. So, when you give the complex exponential as the input, the output is the same complex exponential function multiplied by some gain. Okay, so because of that, if we can write an arbitrary input signal in terms of or a summation of complex exponentials, then it would be easy to compute the output in that case as well. Okay, so that is the goal. So to do or to write the given signal x of t in terms of complex exponentials, that is what we call it as frequency domain representation. Okay, so Fourier series is one particular way in which we can write a periodic signal in terms of complex exponentials. That is what we saw yesterday. Okay, so I told you that any periodic signal, okay, so it can be written as a weighted sum of complex exponentials, that is x of t can be written as sum over ak e power j k omega naught t, where omega naught t is the fundamental angular frequency, and so you write in terms of harmonics of the fundamental frequency, and ak are the Fourier coefficients, Fourier series coefficients. So, so they form an equivalent representation of the signal. So once you have the frequency or Fourier series coefficients, you know everything about the signal. So it is an equivalent representation, and it will be useful to study LTI systems. Okay, so today I will take one example and illustrate how Fourier series can be computed for that particular case, and I will also show you some results from MATLAB how the Fourier series is actually converging. Okay, so I will give that, I will start with that today, and then for the rest of the session we will look at Fourier series in more detail, what are its properties, and using those properties it might be easier to compute the Fourier series. So finding the frequency domain representation of a periodic signal is equivalent to finding the Fourier series coefficients. Okay, so what are the properties of Fourier series which will help us to find these coefficients in a more simpler manner. So that is what we will continue next. Okay, so first I will take an example for to illustrate Fourier series. So let us say x of t is a periodic square wave. Okay, so x of t is of the form periodic square wave. So let us say this is your time and this is your signal. So let us say it is like this. So its on cycle and off cycle have the same duration, and it goes on and on. Okay, so this is the fundamental period. So the fundamental period, we have a notation. So T naught is the fundamental period, right? So now for this signal, let us find the Fourier series and try to understand how the convergence is working. Okay, so now so we know the formula to find the Fourier series coefficient. So you have a sequence of Fourier series coefficient. Okay, so AK is the coefficient for the kth harmonic. So it is nothing but integral over T naught x of t e power minus j omega naught. So omega naught t. So omega naught is nothing but angular frequency, which is 2 pi by t naught e power j omega naught t dt. So if you go ahead and do the integral, so if I can break the integral, so it will be from minus t naught by 2 to minus t naught by 4. You have the value minus 1 e power minus j. Oh, I have to put k omega naught t. Sorry, because I am finding the coefficient for the kth harmonic. So k omega naught t. So please make that note that change. So I am using k omega naught t dt, and again I have some more integrals to finish. So from minus t naught by 4 to plus t naught by 4, the value is 1 e power minus j k omega naught t dt, and then there is one last integral from t naught by 4 to t naught by 2, again goes to minus 1 e power minus j k omega naught t dt. Okay, so again as I said, omega naught is 2 pi by t naught. So when you substitute find the integral and substitute the limits, it is very easy to verify that. So ak will be 0 if k equal to 0. So when k equal to 0, this integral will become 0, and it is sin k pi by 2, the whole thing divided by k pi if k is not equal to 0. So we can write x of t, the square wave, as summation k equals minus infinity to plus infinity, and k not equal to 0, because when k equal to 0, the coefficient is 0. You have ak e power minus or plus j k omega naught t. So we were able to write the square wave in this fashion. So first of all, okay, so let us see, what is that meaning of the square wave is equal to the sum of complex exponential? It means that when you keep adding more and more terms, so the summation on the right hand side is an infinite term summation. Okay, so there are infinite number of terms in the summation. So what we actually mean is that as we add more and more terms, this sum is going to look more and more like the square wave. Okay, so that is what we mean. So essentially, so consider summation up to n harmonics. Suppose I sum only, so let us say I call this as xn of t is sum over k equals minus n2 plus n ak e power j k omega naught t. Okay, so actually I don't have to put k not equal 0, so it's not needed. I know that zeroth coefficient is 0. So now I have summed over only n harmonics. Now as n goes to infinity, that is I add more and more harmonics, we have this this function, which is sum of these m up to n harmonics, it converges to x of t. Okay, so as you add more and more harmonics, the sum on the right hand side will look like your square wave. Okay, so let me illustrate that using some pictures. So now I have shown you a picture. So what the red color function is the square wave, and then the blue color function is the right hand side. But in the right hand side, I control the number of harmonics. So for this particular function, I have only one harmonic. So if I use only one harmonic on the right hand side, I get the blue function. But if I have only one harmonic, it's not going to be a good approximation. So I increase the number of harmonics. So this is 5 harmonics. So if I add 5 harmonics in the Fourier series representation, I get this blue function. It is better, but it is still having ups and downs, and it is still not exactly a square wave. So I add more harmonics. So if I have 10 harmonics, this is what it looks like. So we can see that things are getting better. So if I add more harmonics, the blue curve is going to look more and more like square wave. So for instance, this is with 100 harmonics. So if I have 100 terms on the right hand side, okay, so then the summation looks like this, and then the last one is with 1000 harmonics. So the right hand side, the blue function, which is sum of these Fourier series terms up to n harmonics, here n equal to 1000. So I can clearly see that it is getting a better and better approximation. So if I add more and more harmonics, I will get more and more close to the square wave. Okay, so it is just an illustration, that simple illustration, that by adding more harmonics in your Fourier series terms, you are actually approximating the square wave better and better. Okay, so that is the idea. Now you can still see that in this picture at the point of discontinuity. So when the square wave jumps from 1 to -1 or -1 to 1, you can still that the blue is not a very good approximation. The blue is still away from that square wave. So there is some more details involved here. I will talk about those in when I talk about the convergence. But now these pictures simply illustrate that the Fourier series is actually doing its job. So if I add more and more harmonics, my approximation gets better and better. Okay, so you are able to get a good approximation of the square wave using complex exponential functions. Okay, so it is interesting. Okay, now I'll continue with this Fourier series. So the next important thing is there is an alternative way in which we can represent the Fourier series. So first we have represented Fourier series using complex exponentials, and as we know that the complex exponentials are closely related to, that is, e power j omega naught t is closely related to sin omega naught t and cos omega naught t. So we can actually write the Fourier series in terms of sine waves and cosine waves, sine functions and cosine functions. I will give that derivation now. Okay, so I will show you now how we can do Fourier series representation using sine and cosine functions. So this is called trigonometric Fourier series. So this is an alternative function. So this is again another equivalent representation for periodic signals using sine. Okay, so using sine k omega naught t and cos k omega naught t. So instead of e power j omega naught t, we use sine and cosine functions to write the Fourier series representation. Again, this might be useful in under some other context. So it can be written as so x of t is a periodic signal, again a periodic signal with the fundamental period t naught. Okay, so now we can write or represent x of t as x of t equals a0 plus sigma k equals 1 to infinity bk cos k omega naught t plus k equals 1 to infinity ck sin k omega naught t. So, instead of complex exponentials, we simply replace it with a new set of functions, which is sinusoids and cosines, but they are all related to the complex exponential, right. So, here a naught is nothing but the area under this function over duration t naught, and bk is nothing but you multiply x of t with cos k omega naught t and then integrate, and then ck is integral over t naught x of t sin k omega naught t dt. Of course, I have to do some normalization. So, this is 2 by t naught, 2 by t naught. So, 2 by t naught is multiplying with this integral. So, 2 by t naught integral over duration t naught x of t cos k omega naught t is bk, and ck is 2 by t naught multiplied with integral over duration t naught x of t sin k omega naught t dt. So, this can be obtained, so derivation or the proof is obtained from the complex exponential Fourier series representation. So, we have the complex exponential Fourier series so x of t is sigma over k from minus infinity to plus infinity a k e power j k omega naught t, right. So, that is a complex exponential Fourier series representation, and so this I can write it in terms of 3 different things. So, sigma k equal to minus infinity to minus 1 a k e power j k omega naught t plus k equal to 0 term. So, when k equal to 0, we have a naught e power j into 0 times omega naught t plus the positive harmonics k equals 1 to infinity a k e power j k omega naught t. So, I simply split the summation into 3 parts. One is for the negative harmonics, one is for k equal to 0, the other one is for positive harmonics. So, I can write this as, so a naught, so the 0th harmonic is nothing but a DC function. So, it is a naught times 1 plus I am going to combine these positive harmonics and negative harmonics into one summation. So, this is a k e power j k omega naught t plus a minus k e power minus j k omega naught t. Okay. So, that is the negative harmonics are represented using a minus k e power minus j k omega naught t, and positive harmonics are a k e power j k omega naught t. So, I am grouping these two things under one single summation, right. So, now I can write, so this is a naught plus sigma k equal to 1 to infinity a k into, so I can write this as cos k omega naught t plus j sin k omega naught t plus a minus k times cos k omega naught t minus j sin k omega naught t. Okay, so I am simply writing them in terms of cos and sine, because e power j omega naught t is cos omega naught t plus j sin omega naught t. So now I can group the terms corresponding to cos. So this is plus sigma k equal to 1 to infinity ak plus a minus k multiplied with cos k omega naught t plus sigma k equal to 1 to infinity ak j times ak minus j times a minus k multiplied with sin k omega naught t. So we let's call this ak plus a minus k as bk and j times ak minus j times a minus k as ck. So bk is ak plus a minus k, but ak I know that it is integral over t naught 1 by t naught x of t e power minus jk omega naught t dt plus a minus k is again 1 by integral over t naught x of t e power plus j k omega naught t dt. So this can be written as 1 by t naught integral over t naught x of t times e power j k omega naught t plus e power minus j k omega naught t dt, but this is nothing but 2 times cos k omega naught t, right. So this is bk is nothing but, so that 2 factor I can take it outside, integral over t naught x of t cos k omega naught t dt. So similarly we can verify that this is what we have. Okay, so this is the trigonometric Fourier series. So the signal x of t we were able to write it as a naught plus some coefficient bk times cos k omega naught t sum over all k, and then there is another coefficient ck multiplied with sin k omega naught t, and I am summing it over all the possible positive values of k, right. So this exactly the trigonometric Fourier series where the bk is given by 2 by t naught multiplied with integral over t naught x of t cos k omega naught t. Similarly you can verify that the ck, which is j times ak minus j times a minus k is given by 2 by t naught integral over t naught x of t sin k omega naught t dt. So trigonometric Fourier series we have derived using the complex exponential Fourier series. So this is also an important representation. You can write a periodic signal using sine functions and cosine functions. Okay, so this is called trigonometric Fourier series, which we obtained using complex exponential Fourier series. Okay, so now comes the important part of this session where we discuss the properties of Fourier series. Okay, so there are several important properties related to Fourier series. So we will discuss them. They will be useful in computing Fourier series of certain functions. They will be helpful in interpreting the Fourier series representations and so on. Okay, so we will discuss each property, and then later you will see the importance of these properties. Okay, so next topic is properties of Fourier series. Okay, so again at the end of the first hour, we will have a question and answer session. So I will continue now. After 1 hour, I will stop and then we will clarify any questions, and then after that we will go to the next hour. Okay. Okay. So now, so consider this sequence. Okay. So now, so now x of t again is periodic with fundamental period t naught, and the Fourier series is x of t is sigma k equals minus infinity to plus infinity a k e power j k omega naught t. So the coefficients a k, where k is from minus infinity to plus infinity, k is set of integers. Okay, so k is belongs to the set of integers, both positive and negative side. So this set of coefficients give an equivalent representation of the signal. So now in shorthand, I would like to say x of t, I will use double arrow, right, fs for Fourier series. You have Fourier series coefficients ak. Okay, so x of t has Fourier series representation using these coefficients ak. So once I know the coefficients, I know the x of t. Okay, so they are equivalent representations. Okay. Now this is my shorthand notation that this is the CT signal, continuous time signal. This is the Fourier series coefficients, set of Fourier series coefficients. They are equivalent representations of the same thing. Okay, so now let us look at the property. The first property is linearity. Okay, so Fourier series representation satisfies some linearity property. Okay, so suppose x of t and y of t have are two periodic signals with same period t naught. Okay, so let us say x of t has Fourier series coefficient ak. So it essentially means that x of t is sum over k ak e power j k omega naught t, and let us say y of t has its own Fourier series coefficients. Let us call them as bk. So that means y of t equals sigma k equals minus infinity to plus infinity bk e power j k omega naught t. Now the linearity implies x of t plus y of t. If I try to find the Fourier series coefficients, it will be nothing but ak plus bk. So that is straightforward, right? So x of t has Fourier coefficients ak, y of t has Fourier coefficients bk, and if I add the two signals x of t and y of t, the Fourier series of the sum is nothing but the sum of the Fourier coefficients. So, AK plus BK will be the Fourier series coefficients for the signal x of t plus y of t. It holds in more general. So, alpha times x of t plus beta times y of t has Fourier series coefficients alpha times AK plus beta times BK. So, essentially it means that this is the coefficient corresponding to the kth harmonic. Kth harmonic. Okay, so that is very straightforward. Simply see, if I multiply x of t by alpha, so it simply multiplies the Fourier coefficients by alpha, right. So, similarly if I multiply y of t with beta, so it simply multiplies the Fourier coefficients with beta. So, when you sum, you just sum these Fourier coefficients. So, this is straightforward. So, it is important property which is called linearity. Property 2 is related to symmetry of the Fourier coefficients. Okay, so it is called symmetry if x of t is a real signal. So, instead of so in Fourier analysis we allow complex signals, right, because nevertheless the complex exponential itself is a complex signal, right, e power j k omega naught t is a complex signal. So, in our analysis everything can be complex. So, the x of t can be itself can be a complex signal. We never made any restrictions on that. Now, we are saying that instead of complex, if x of t is a real signal, that is the imaginary part is 0, then if you look at its Fourier coefficients, then the kth harmonic Fourier coefficient is nothing but the negative kth Fourier coefficient, but you have to do conjugate. Okay, so this is called conjugate symmetry. So, star essentially I use for conjugation. So, it essentially means Fourier series coefficient of kth harmonic is equal to the conjugate of Fourier series coefficient of minus kth harmonic. Only if x of t is real. Okay, so if x of t is not a real signal, if x of t is a complex signal, then there is no symmetry. There is need not be any symmetry properties. But what we are saying is, if x of t is a real signal, then the coefficient corresponding to Fourier series coefficient corresponding to the kth harmonic and is equal to the conjugate of the Fourier series coefficient of negative kth harmonic. For instance, if you go and look at our example, so I did a square wave example, right. So, in the square wave example we found Fourier series coefficients, right. So, we can clearly see that the coefficients are itself are real, and you can see that the coefficient corresponding to the negative kth harmonic is the conjugate of the coefficient corresponding to the positive kth harmonic. Okay, so that is, since they are real, we have, so that property is satisfied for that real signal. Okay, so that is what I wanted to show. Now we can verify this easily. So let us prove this proof for this property. So x of t is real. Okay, so now x of t is written as minus infinity to plus infinity ak e power j k omega naught t. Now x conjugate of t, I conjugate both sides. So this is nothing but sum over minus infinity to plus infinity ak e power j k omega naught t, the whole thing you conjugate. Okay, so now you some certain complex things and then you conjugate, it is equivalent to conjugating each quantity and then summing, okay, because conjugation is linear. So, I mean it is not affected by interchanging the summation and conjugation. So, I conjugate each term and sum. So, now each term, so it is a product of two terms, okay. So, I have to take the product conjugate of the product, it is equivalent to you multiply, you take the conjugate of each quantity and then take the product. So, when you conjugate a product of two complex numbers, it is equivalent to conjugating each complex number and then taking the product, okay. So, that is what I am using now. So, this is equal to k equals minus infinity to plus infinity a k conjugate. If I conjugate e power j k omega naught, it will become e power minus j k omega naught. Okay, so this is x star of t. We know that, so this, so since x of t is real, x of t is equal to x star of t. So this is the Fourier series representation of x star of t, and we already saw the Fourier series representation of x of t. So we have, so x of t is sigma k equals minus infinity to plus infinity a k e power j k omega naught t, that is equal to, if you look at the other series, it is minus infinity to plus infinity a k conjugate e power minus j k omega naught t. Okay, so now they are the two summations represent the same thing. So the coefficient wise they should be identical. Okay, so that is another important thing. So the Fourier series representation is unique. So if two signals are same, then the Fourier coefficients have to be the same. So the Fourier series coefficients for x of t and Fourier series coefficients for x star of t, they have to be the same. But now if you look at this Fourier series representation, so the coefficient multiplying kth harmonic, so the coefficient multiplying kth harmonic in both sides have to be the same. So the coefficient multiplying kth harmonic should be same in both LHS and RHS. So now the coefficients of the Fourier series should be same in both expressions. So in both, in the left hand side, the coefficient corresponding to kth harmonic is AK, and in the right hand side the coefficient corresponding to kth harmonic is A minus k conjugate, right, because A k conjugate is multiplying with negative kth harmonic. Okay, so what will be multiplying with the positive kth harmonic will be A minus k, right. So A minus k conjugate. Okay, so ak is the coefficient for kth harmonic in the left hand side. Similarly, the kth harmonic in the right hand side is e power j k omega naught. What will be the coefficient multiplying e power j k plus j k omega naught is a minus k conjugate. So these have to be identical to each other. Okay, so that is from directly comparing the coefficient. So this is what we call it as conjugate symmetry. Okay, so the coefficient for kth harmonic is the coefficient corresponding to minus kth harmonic conjugate. Okay, so this is the symmetry property. We will see couple of more properties. Okay. Okay, so the next property is related to time shifting. Suppose x of t has Fourier series coefficients ak. Now let us delay the signal. Let us say I delay it by some t naught. Okay, so delay or time shift, that will have Fourier series coefficient ak e power minus j k omega naught t naught. Okay, so that is the property. So if I know the Fourier series coefficients for a signal x of t, then the Fourier series coefficients for a delayed signal. Okay, so x of t minus t naught is nothing but the delayed version of x of t. For that, the Fourier series coefficient is obtained simply by taking the original Fourier series coefficients ak, multiplying by this complex phase, that is e power minus j k omega naught t naught. Okay, so this is a phase shift. This is a delay. So delay in the time domain leads to phase shift in the frequency domain. So this is another important result. So delaying a signal in time domain leads to phase shift in the frequency domain. Okay, so let us prove this. It is very easy. The proof is straightforward by using the Fourier series representation. So x of t is sigma over k ak e power j k omega naught t. So now replace t with t minus t naught. T minus t naught. So I will have x of t minus t naught on the left hand side. This is summation ak e power j k omega naught t minus t naught. Okay, so now this is sigma over k ak e power minus j k omega naught t naught multiplied with e power j k omega naught t. Okay, so this is the Fourier series coefficient. So this is the Fourier series coefficient for kth harmonic. Remember that this is the kth harmonic. So the Fourier series coefficient which multiplies the kth harmonic frequency is ak e power minus j k omega naught t naught, and that is what we said, right. So the Fourier series coefficient for x of t minus t naught is given by ak e power minus j k omega naught t naught. Okay, so that is somewhat straightforward. Let us look at few more properties. Property 4, it is called time reversal. Okay, so let us say x of t has Fourier series coefficients given by the set ak. Now so x of minus t, so time reversal is you change the time axis by multiplying with minus 1. Okay, so x of t is the original signal and x of minus t is time reversed signal. So whatever happened on the positive side will happen on the negative side, and negative side will go to the positive side. So, this is the time reversal. So, once I do this signal, so for instance, so let us say x of t looks like this. Now, x of minus t will look like this. It will get reversed. So, whatever was on the positive side, it will go to the negative side, and whatever is on the negative side will come to the positive side. So, if I time reverse it, what happens is, interestingly, the Fourier series coefficients also get reversed. So, whatever was on the kth harmonic, it will go to the negative kth harmonic. So, the coefficient whichever multiplied with the kth harmonic in x of t, the same coefficient now will multiply the negative kth harmonic in x of minus t. Okay, so this is easy to verify itself. Okay, so easy to verify. So it's similar to what we did here. So here we replace t with t minus t naught. The same thing you can do here, t with minus t. If you replace t with minus t, then you will get this result. Okay, so this is straightforward. So I'll go with that. So again, let us go to the another symmetry property for a symmetry. Okay. So if x of t is an even signal, so an even signal is symmetric about origin. So x of t, that is x of t equals x of minus t, then Fourier coefficients also symmetric. So ak is also even. So ak equals a minus k. So what do I mean by that? So we know that x of t has Fourier series coefficients ak, x of minus t has Fourier series coefficients a minus k. We know that x of t is equal to x of minus t in even. So ak has to be equal to a minus k. So for an even signal, the Fourier series coefficient corresponding to plus kth harmonic and negative kth harmonic are identical. Okay, so again we can look at this here. Okay, so if we go back to the square wave example which we saw earlier, yeah. So the square wave is a symmetric function with respect to 0, right. So x of minus t is equal to x of plus t. So it is symmetric. Now if I look at the Fourier coefficients, it is sin k pi by 2 to by sin k pi. So easily you can verify that the coefficient corresponding positive kth harmonic and negative kth harmonic are both identical. So sin k pi by 2 divided by k pi will be same whether k is positive or negative. Okay, so this is also an even function. Okay, so that is what we see here. So for any even signal, the Fourier series coefficients will be symmetric in the sense the coefficient corresponding to minus kth harmonic and coefficient corresponding to plus kth harmonic, they are the same. Okay, so I will discuss one last property and then we will discuss question and answers. Okay, so property 5 is time scaling. So I will show what do we mean by time scaling. So for instance, x of t is this function. Let us say for instance x of t starts from minus 1 to plus 1. Now x of 2t is nothing but the same function, but it is compressed now. So minus 1 by 2 to plus 1 by 2. So when you scale the time axis, so when you compress it or expand it, that is what we call it as time scaling. So we compress the time axis or expand the time axis. So x of 2t is a compressed version of x of t, while x of t by 2 is expanded version of x of t. So time scaling is essentially what we mean by that. So let us say x of t has Fourier series coefficients ak, then let us say we time scale by alpha. Okay, so let me write the Fourier series representation now itself. So x of t equals sigma k ak e power j k omega naught t. So we do the time scaling. So time scale by alpha. So x of alpha t is nothing but sigma k ak e power j k omega naught times alpha t. So this is again I can write it as ak e power j k omega naught alpha t. So the Fourier series coefficients are the same. So x of alpha t. So this is the Fourier series representation of Fourier x of alpha t has same Fourier series coefficients as x of t. Only thing is the fundamental frequency now has changed. Okay, so fundamental frequency has now changed from to omega naught to alpha omega naught. Okay, so essentially if I time scale, if I stretch the signal or compress the signal, the Fourier series coefficients are going to be the same. Only thing is the fundamental frequency is now different because now I have compressed the time axis, the fundamental period and the fundamental frequency will change. So if I want to draw an example, for instance, let us say this is the periodic signal. So x of t is like this. So again when we talk about Fourier series, we have to talk about periodic signals, right. So 1 minus 1 to 1 3 5 minus 3 and so on. So now if I compress that, it will go from minus half to plus half to 3 by 2 and then there is 5 by 2 and so on. It is the same triangle wave, now that it is a compressed version of original triangle wave, right. So and go on, they go on. So the first one is the periodic signal with time period 2, the second one is same, it has the same structure but the time period is now 1. Okay, so when we compare the Fourier series coefficients for x of t and x of 2t, they are identical. Only thing is now the fundamental period has changed. So that is what we mean by that. Okay, so x of alpha t has the same Fourier series coefficients as x of t, but only difference is since we have compressed the time axis, the fundamental frequency will now be alpha omega naught instead of omega naught. Okay, so that is what this property means. So these properties are important in the sense they will be able to help us to find the Fourier series coefficients of some signals. Again, these Fourier series coefficients are going to help us in representing the signals in terms of complex exponentials, and again that is going to help us in studying the LTI systems. So when you give the complex exponentials as an input, you will again get back the same complex exponential, of course with some gain. Okay. So I will stop here and I will answer some questions. So we will continue further to look at some more properties of this Fourier series representation, and then finally I will talk about some convergence guarantees. So, when can you use Fourier series? Can you use Fourier series for any arbitrary periodic signal, or are there some conditions only under which you can use Fourier series? Okay, so I will look at that at the end of this session. Okay, so I can answer some questions now. Okay, so one of the question is the complex exponential Fourier series better than or more useful than trigonometric Fourier series? Which is more better, which is more useful? Okay, so it depends on the application. For instance, when we are talking about LTI systems and study of LTI systems, you can complex exponential Fourier series is more useful. But there are also some problems in physics, vibrations, to study the vibrations and everything. There also people use Fourier series representations. Their trigonometric Fourier series are more useful. Okay, so that is the difference. So complex exponential Fourier series is useful to study LTI systems, while trigonometric Fourier series is useful to study some other problems in physics where something like vibration of a string or some things like that, they use trigonometric Fourier series. So one of you have asked about differentiation and integration property of Fourier series. I will talk about them next. Okay, so I will do that next. Another thing is about Gibbs phenomenon. So right now this Gibbs phenomenon doesn't come into the picture. Okay, so for Fourier series representations, Gibbs phenomenon is not an is does not come into the picture. Okay, so when we talk about Fourier transforms, there are some issues in like Gibbs phenomenon, but Fourier series don't have any Gibbs phenomenon related things. Okay, one of you have asked why Fourier transform is so important in signal processing. Okay, so again, as I said, lot of systems we deal with in electrical engineering, they are all linear time invariant systems. For instance, your circuits, when you want to go analyze your circuit, resistor, capacitor, inductor. Okay, so that is an LTI system. So when you have linear time invariant systems, Fourier series and Fourier transforms are very natural tools to study them, because the complex exponential functions are the eigenfunctions of the LTI system. Meaning eigenfunction essentially means when you give the signal as the input to the LTI system, you get the same signal except for some multiplication factor, right. So that is like an eigenvector eigenvalue thing, right. So in terms of when we talk about systems, we call it as an eigenfunction of a system. So this function you give as an input, you get the same function as the output, complex exponentials, right. So that is a nice thing. So the goal is to represent the signal, any arbitrary signal, in terms of complex exponentials, as I said. So that is why we study Fourier transforms, and we will talk about one application of Fourier transform in the next session. So we will take up an important application in communication system and show that the Fourier transform concepts and frequency domain representation we studied using Fourier series and Fourier transforms will be directly applicable to build a communication system. I will explain how to build, how a particular communication system is built using these Fourier transform ideas. Okay, I will talk about the application in the next session. I don't want to talk about it now, because before I want to talk about the application, I want to talk about some of the properties, because the application, to understand the application, you need to understand the properties. Okay. So anything else? Property 6, which I call it as multiplication property. Okay, so let's say x of t has Fourier series representation AK. Let's say y of t is Fourier series representation using these coefficients bk. Now x of t times y of t. So I take the product and find the Fourier coefficients of Bk. So the product, let me call it as Ck. This Ck is nothing but this Ak convolved with this sequence Pk. So you have the sequence, right? Ak is a sequence of Fourier coefficients. So it is indexed from k running from minus infinity to plus infinity. So it is a set of it is like a sequence. It's a discrete time sequence where you can think of k as the time index. In this case, it is the harmonic index. So you can think of this as a sequence indexed by its harmonic index. Similarly, Bk is a sequence. Now to find the product of the Fourier series of the product of these two signals, you have to convolve these two sequences. Okay, so this is convolution. So remember that when you take the product of two signals, the Fourier coefficients are not products. The Fourier coefficients have to be convolved. Okay, so let me try to illustrate that property, why that is happening. So now so x of t is sigma over k ak e power jk omega naught t. Let us say y of t is sigma over k bk e power jk omega naught t. So I can just use a temporary summation. Okay, so I am going to call this as bl e power j l omega naught t. Okay, so this is just k is just a temporary variable. It's a variable of the summation. Instead of k, I am going to use l because for x of t I am using the summation using k index k, and y of t I am going to use a different index l. Okay, so because I am going to take a product now, so x of t y of t is nothing but sigma over k ak e power j k omega naught t multiplied with sigma over l bl e power j l omega naught t. Sigma over k sigma over l ak bl e power j k plus l omega naught t. Okay, so I am going to introduce a new variable, change of variables. I am going to substitute k plus l equals m. So that is essentially I am going to substitute k equals m minus l. Okay, so m minus l. So and then I am going to write the summation in terms of m and l and remove the index k. So sum over l, sum over m, ak I am going to write it as, since k is m minus l, I am going to write m minus l bl e power j k plus l is m omega naught. Okay, so this one does not depend on l. Okay, so e power j m omega naught t, I can take it outside the summation of l. Okay, so for instance now I can take it over m a of e power j m omega naught t and sum over l a of m minus l v of l. Okay, so since one of the terms does not depend on l, I take it outside that summation and then keep only the terms which depend on that index l. Okay, so this is what I have. So this is the coefficient corresponding to mth harmonic, corresponding to mth harmonic. So this is the mth harmonic. This is the Fourier series representation of the product. So what we had was just the product of these two signals x of t times y of t, right. So, the mth harmonic term, the coefficient corresponding to mth harmonic is that inner summation over L a of m minus L B L, right. So, Cm is the mth harmonic coefficient sigma over L a of m minus L B L. Okay, so that is the mth harmonic coefficient. So, this is nothing but am convolved with bm. So, this is nothing but convolution sum. So, this is the convolution sum. Okay, so this is the convolution in the discrete time domain. So, we find that to find the harmonic, the coefficients of the product of two signals, you have to take the Fourier coefficients of each signal and convolve those Fourier series coefficients with each other. Okay, so that is how you will get the product. So, this is an again multiplication is an important property. Okay, so now let me talk about next important property, which is Parseval's theorem. It is called Parseval's theorem. So, what it does is it talks about the squared value of the signal. Okay, so now let us say x of t has Fourier series representation ak e power jk omega naught t. Now, Parseval's theorem says is that integral over t naught 1 by t naught mod of x of t square dt. So, the area under the curve is nothing but sum of these sequences k equals minus infinity to plus infinity mod ak square. Okay, so that is what Parseval's theorem is. Okay, so the energy or the average energy of the signal over the duration t naught is nothing but the sum of squared values of the Fourier series coefficients. Okay, so 1 by t naught integral x of t square dt over the duration t naught is the fundamental period, right. So, remember that we always talk about t naught is 2 pi by omega naught. So, omega naught and t naught are related to this way. So, one is the time period, the other one is the equivalent angular frequency. So, time you would have been using the regular frequency, which is 1 by time period, but we are using a multiple of that. So, omega naught is nothing but 2 pi times f naught. F naught is the fundamental frequency. Okay. So, anyway, so the proof is somewhat straightforward. So, you have the signal x of t sigma over k ak e power j k omega naught t. Now, x star of t, the conjugate, you conjugate on both sides. Again, I am going to use a different variable for the summation a l star e power minus j l omega naught t. Okay. So, ak, so I take the product of these two. So, x of t mod of x of t square is nothing but x of t times x star of t. So, this is sum over k sum over L ak al star e power j k omega naught t e power minus j l omega naught t. Now I integrate both sides. So integral over T naught mod of x of t square dt is sigma over k sigma over L a k a L star and integral over T naught e power j k omega naught t times e power minus j L omega naught t dt. So the important thing to realize is what we saw from the last session. This integral, okay, so let me get some space here. So this integral will be 0 if k is not equal to L. If they are same, then the integral value is T naught. Okay, so then it means that only when k and L are same you have, so it will be a k multiplied with a k star times T naught. Okay, because when L is not equal to k, then that integral is 0. So those terms are zeros. So you have to include only those terms which are non-zero in the summation. So this is T naught times sigma over k mod of a k square, right. So it means that 1 by T naught integral over T naught mod of x of t square dt is sigma over k mod of a k square. Okay, so this is the Parseval's theorem. So the average energy of the signal in the interval T naught is simply obtained by summing the squared values of the Fourier series coefficients. Okay, that was the property 7. Now let us look at property 8. Differentiation and integration. So we will look at those two properties and then we are almost done with the properties. Then we can talk about convergence of Fourier series. Property 8 is differentiation. Let us say x of t has Fourier series representation using Fourier coefficients ak. Now you have the derivative of signal x of t that will have Fourier series coefficients ak multiplied with jk omega naught. So the kth harmonic coefficient for the derivative is nothing but the original signal's coefficient ak multiplied with this jk omega naught. So we can easily verify this property. Okay, so proof is simple. So x of t is sigma over k ak e power j k omega naught t. I take the differentiation on both sides. So I can take the differentiation inside the summation. So this is d by dt e power j k omega naught t sigma over k ak. If I differentiate that, so I will get j k omega naught times e power j k omega naught t. So this is the Fourier coefficient for kth harmonic, right. So ak times jk omega naught, that is the thing which multiplies the kth harmonic e power jk omega naught t. So the Fourier coefficient is ak times jk omega naught. So that is what we have initially, right. So we are at the last property, which is property 9, I think, which is the integration property. So the thing is, if we integrate, so for instance, let x of t be sum over k ak e power jk omega naught t. So let us say this is a naught plus sum over k not equal to 0 ak e power jk omega naught t. So I take out the term corresponding to 0th harmonic, that is called the DC frequency, DC frequency. So and then all the remaining things I will group in the summation. Okay, so a naught plus sum over k not equal to 0 ak e power jk omega naught t. So now if I do the integration, suppose let us say I define this integral. So let us say let y of t be the integral from minus infinity to tau x of tau, sorry, integral limits are minus infinity to plus t x of tau d tau. Okay, so this integral is finite only if a naught is 0. Okay, so a naught is like a constant, right? The complex exponentials, when you integrate them, their average value is 0, so that is not a problem. But a naught is a fixed constant. So if you integrate it over the infinite interval, if you integrate the constant value over the infinite interval, then that area will be infinity, right? So y of t is well defined only if a naught is 0. Okay, so y of t is well defined only if a naught equal to 0. Otherwise, the integral is unbounded. So otherwise, integral is unbounded. So it has very large value, or it is basically, it can go to infinity. Okay, so in our case, so we restrict ourselves to a naught equal to 0. So that is the DC value of the signal is 0. So let us assume a naught equal to 0. So x of t is sigma over k not equal to 0 ak e power jk omega naught t. So I take the integral minus infinity to tau, sorry, minus infinity to t x of t dt. So this is sum over k not equal to 0 ak integral minus infinity to t e power j k. So I should use the tau as the temporary variable, right? K omega naught tau d tau. So if I do this, I get, since they are all periodic with respect to period t naught, so this will be ak 1 by kj omega naught e power j k omega naught t. Okay, so the integral over every period is 0. Okay, so all you have to do was, you can do the integral from 0 to t instead of minus infinity to t. Okay, so essentially from minus infinity to 0 you take the integral. So it is basically integral over, it completes if the duration is one time period, so the integral will be 0. So all you need to do was so because of that, so you will have a finite value over this integral. Okay, so now y of t, which is integral from minus infinity to t x of tau d tau, will have the Fourier series coefficients ak divided by jk omega naught. Okay, so this is the Fourier series coefficients of the integral. So essentially, remember that so an alternative view of integration and differentiation. So alternative view of differentiator. So if I give a signal e power j k omega naught t as the input to the differentiator, what I will have is I will have j k omega naught multiplied with e power j k omega naught t. So differentiator gives a gain of j k omega naught to the complex frequency, to the complex exponential, to the kth harmonic, to the kth harmonic. So the gain is proportional to k. Okay, so higher harmonics get higher gains, smaller harmonics get smaller gains. So differentiator is more like, for high frequency components it gives high gains, low frequency components it gives low gains. So differentiator is more like a high pass filter. So high gain for high frequencies or higher harmonics, small gain for small harmonics or small frequencies. So the differentiator is acting like a high pass filter where it gives higher gain for higher harmonics and lower gain for lower harmonics. On the other hand, if you look at the look at the integrator, it is doing the opposite. Okay, so intuitively, if you think about it, differentiator, when the signal is changing fast, okay, so the differentiator is like seeing what is the slope of the signal, right, at a given point. So if the signal is changing very fast, then it will give a higher slope, right. So the higher slope will means differentiator output will be high. Okay, so if the signal is changing fast, you will have high outputs for the differentiator. When on the other hand, if the signal is changing very slowly, very smoothly, then differentiator output is going to be small, right, because the signal is not changing fast enough. So that is the intuitive way. So differentiator is more like high pass filter, and integrator is more like a low pass filter. So if you give the e power j k omega naught t as the input to the integrator, so what you will get is e power j k omega naught t by j k omega naught. So the gain is proportional to 1 by k. So gain is proportional to 1 by k. So low frequencies get high gain, high frequencies get low gain. So the integrator is like a low pass filter. So somehow we are able to get an intuition of how the integrator is behaving and differentiator is behaving for different frequencies by using these Fourier series ideas, right. So integrate is more like when you integrate a function, it will actually smoothen things out. What some rapid changes will get smoothened out by the integrator. So integrator is like a low pass filter, while differentiator is a high pass filter. It amplifies the quick changes. So if things are changing quickly, it produces high outputs. So that is the interpretation we can get from Fourier series ideas. Okay, so now I am going to talk about the last point or the another important topic, convergence of Fourier series. So the Fourier series is will converge to the true signal. You remember that we saw that square wave. We were able to write the Fourier series representation of the square wave and take more and more terms in the Fourier series representation, higher and higher harmonics, and as we sum higher and higher harmonics, we were able to get closer and closer to the true signal, right. So the convergence happens for the square wave, but what are the conditions for convergence? Okay, so can the Fourier series converge to the true signal x of t under any case? No, it is not. Okay, it has to, x of t signal x of t has to satisfy some conditions, only then we are guaranteed to have convergence. I will talk about those conditions now. Okay, so conditions under which Fourier series converge to the original signal. So Fourier series representation, remember that your xn of t, so x of t, you can find the Fourier coefficient, so x of t. So for instance, the kth harmonic, so ak is 1 by t naught sum over t naught x of t e power minus jk omega naught t dt, right. So you can find ak and compute this Fourier series up to n terms or harmonics. So xn of t is sum from minus n to plus n ak e power j k omega naught t. So we can compute this because there are only finite terms in the summation, we can actually do it, right. So now we compare this xn of t and x of t. Will they be close? Will they be similar, right? So now the question is, we can say that under the following conditions called Dirichlet conditions, Dirichlet conditions, we have xn of t converge to x of t as n goes to infinity at all points of t where x of t is continuous. So for instance, x of t itself has some jumps. For instance, in square wave, x of t has jump, right? It comes from 1 to -1 and -1 to 1 and so on. So there are some points of discontinuity. So at those points of discontinuity, we cannot guarantee convergence. But there are other points, right? Apart from that discontinuous points, there are other points in which the function is continuous. Okay, so it is discontinuous only at certain points. So all the points in which the function is continuous, we are guaranteed that the Fourier series representation will converge to x of t if the Dirichlet conditions are satisfied. So what are those Dirichlet conditions? Okay, so let me discuss them. now. Okay, so Dirichlet condition, 3 Dirichlet's conditions. So all of them has to be satisfied. So all 3 need to be satisfied or must be satisfied for Fourier series convergence. For Fourier series convergence. So what are those conditions? First condition is integral over T naught, absolute value of x of t dt. This integral should be finite. Okay, so this is the first condition, that is the absolute integral of the absolute value of the signal of absolute value of signal over duration T naught should be finite. So when I take the absolute value of the signal and integrate it over duration T naught, that integral should be finite. So that is the first Dirichlet condition. So that must be satisfied if you want convergence of Fourier series. Okay. Now there is another condition. The second condition is x of t should have finite number of maxima and minima. Over the interval T naught. Okay, so see, the function can have many, so you can, so what is the maxima, right? So let me draw a picture. So for instance, so this is a maxima, this is a minima, this is a maxima, minima, and so on. Right, maxima is the point at which it reaches a local maxima, and the minima is the point in which the function reaches a local minimum. So if you have some squiggly function like this, so whenever it turns around, so it is going up and then it comes down, right. So that turning point is a maxima, and then when it comes down and it again goes up, right. So that is a minima. So if a function has finite number of, the function should have my finite number of maxima and minima within the interval T naught. So that is the second Dirichlet conditions, and then let us see the third Dirichlet conditions. X of t should have finite number of jumps, should have finite number of discontinuity or jumps over the interval T naught. So T naught is the fundamental period, right. So within one period it should have finite number of jumps. Within one period it should have finite number of maxima and minima. Within one period it should be absolutely integrable. Okay, so these three are the Dirichlet conditions. If these three conditions are satisfied, then Fourier series converges. Okay, so that is what we said, right. So when the following three Dirichlet conditions are satisfied, when the following three, so when the following Dirichlet conditions are satisfied, then the Fourier series representation converges to the true signal x of t, otherwise it won't converge. Okay, so now I will give you some examples of functions which will violate these Dirichlet conditions. Okay, so that is also important, so that you should be able to appreciate why, what is the wrong with those functions. Okay, so examples which violate Dirichlet conditions. Okay, so first example is x of t is 1 by t 0 less than or equal to t less than or equal to t naught. Okay, so it repeats every t naught, but so it is 1 by t. So it looks like this. So this is my t naught. So at t naught again it goes up to t naught, it repeats. Okay, so this is the function. It looks like the inverse function. So 1 by t, as t goes to 0, it goes to infinity, right. So this function actually goes to infinity. So this function will violate the first Dirichlet conditions. So 1 by t is unbounded as t goes to 0. So t goes to 0, 1 by t goes to infinity, right. So this function is not absolutely integrable. So if you try to find the area of this function 1 by t, you won't be able to find it because it is going unbounded, right. So this violates the first conditions. So violate condition 1. Now let us see how the second function x of t is sine of 1 by t 0 less than or equal to t less than or equal to 1. Okay, so and then it repeats. So t naught equal to 1. So it repeats after every 1 second. So whatever happens in first 0 to 1 second, it repeats. Okay, so now let us see what happens to this function in 0 to 1. Sorry, this is 1, this is 0. So the same thing will repeat. So at t equal to 1, see, it starts slowly, but as t approaches, it goes faster and faster. Okay, so maybe I will erase this and draw. So sine 1 by t, when t is close to 1, it is sine 1. It looks like a sine wave, but as t goes to close to 0, the frequency gets fast because we are talking about 1 by t, right. So it goes and oscillates very fast, starts oscillating as fast as t goes to 0. As t goes to 0, sine 1 by t oscillates very fast. So it goes up and down a lot when you are approaching t equal to 0. So it means it has lot of maxima and minima. So it violates the second condition. Second Dirichlet condition. So this one, so you can't find the Fourier series representation for x of t. So this sine 1 by t you can't find. And the last function is like this. So infinite number of discontinuities. So infinite number of jumps. So let us get a function which will have infinite number of jumps within the first time period. Okay, so let's say the time period again is 0 to 1. So let's say this is 1 by 2, this is 1 by 4, 1 by 8, 1 by 16. So what this function is, let's say it starts at 1, at 1 by 2, until 1 by 2 you have height 1 by 2, at 1 by 2 you have height 1 by 4 plus 1 by 4. You jump, basically the jump is 1 by 4. So, this is 1 by 2. You jump by a factor of 1 by 4 and you maintain at that jump. At 1 by 4, you jump by 1 by 8 and then you maintain that until 1 by 8. At 1 by 8, you jump by 1 by 16 and so on. You keep jumping. Okay, so 1 by 16, then 1 by 32, 1 by 64 and so on. So, you keep jumping. So, as you go smaller and smaller close to 0, you will have more and more jumps. Okay, so 1 by 2, 1 by 4, 1 by 8, 1 by 16, 1 by 32 and so on. So, you keep jumping at 1 by 2 power n. Okay, so as n goes to infinity, you will have more and more jumps. So, this function, this staircase kind of function, this will also won't have Fourier series. So, this will violates third condition. So, we have to understand when the Fourier series will converge. So, this gives some picture of I mean we gave some conditions and then and gave some examples of when those conditions are violated, what kind of functions. So, with this I will open up for questions. So, with this we conclude the Fourier series discussion. So, Fourier series is a way of writing a periodic signal in terms of complex exponential functions. Next session we will look at Fourier transforms, which is applicable in more general case. So, it will work for even for aperiodic signals. So, if things are not repeating, we can still write fine frequency domain representation of signals. So, that is what Fourier transform will look. Fourier transform will give us. So, we will look at properties of Fourier transform and then one application of Fourier transform in communication systems. So, with that we will conclude the next session, but this session I will answer the questions now. Okay. So, one question is Fourier series and Fourier representations are useful for LTI systems, linear time invariant systems. The question is Fourier analysis will be useful for linear time varying systems. Okay, so for a time varying system, can we still do Fourier analysis? I think it depends on how we analyze time varying systems. Okay, so right now I don't have any particular example where we can extend the Fourier analysis to time varying systems. We can use some approximations, time varying systems. Even if the system is time varying, we can do some approximations that over some duration of time things are not changing. Okay, so that kind of systems that kind of analysis we do in wireless communication. Okay, so even though when we are moving, when we are speaking on the phone, we are moving, things are changing, right? We are moving our phone from one location to another location. So, things are changing, it is a time varying system, but we will approximate using time invariant systems. So, that in a very small time interval, suppose even though I am moving, if I consider a duration of 1 millisecond, within 1 millisecond I may not have moved much. So, within 1 millisecond I can assume that things are time invariant and then try to do the Fourier analysis using that. So, in wireless communication we do that. So, we approximate time varying system using time invariant systems and then use Fourier analysis there. Okay.
What is the significance of Parseval's theorem in communication?
Parseval's theorem. Okay, so it simply shows that the energy in the time domain is preserved in the frequency domain also. So that is the idea. So I mean, it is in specific things like communication. I mean, it is just shows that by going from time domain to frequency domain, you don't lose any energy or any power. Okay, so that is what it shows. So that is all the theorem is. Okay, so I mean, there is no specific application or such. I mean, it is an important result in the sense by going from one domain to another domain you are not losing anything, right. So that is the main idea. Okay, so JNTU ACEP. Good evening.
Why don't we apply Fourier series for periodic signals?
We don't, it won't work basically. See, the mathematics, when we derived the Fourier series representation, we assumed that it is periodic and you have a fundamental period and then you have harmonics and so on, right. So when we made the derivation, we assumed that it is a periodic signal. So without those assumptions, it won't work. So that is why we have to use Fourier transforms. So when we derive the Fourier series itself, we made an assumption that the signal is periodic. Without that assumption, the derivation will not work. So we have to use Fourier transforms, which will be discussed in the next session. Periodic impulse train, I will discuss that in the next session. Okay, so that is an important question. So we will encounter that. So I will talk about that in the next session. So the same principle can be used. So I will take an example of the impulse train and find the Fourier representation for the impulse train. Okay, so I will do that in the next session. It is an important thing, so I would like to explain it in the class itself. Okay, so I will do that in the next session. Anything else? Okay, I'll stop now and then we will continue in the next session about Fourier transforms. Okay, thank you.